Hello everyone, and welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Rula Deeb. I'm a Senior Principal at Geoscience Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar today will consist of a brief overview of SERDP and ESTCP, followed by a list of upcoming webinars in the series. After our brief opening remarks, we will transition to the technical portion of the webinar. The event today features two presentations on realistic expectations for geophysics when used for site characterization and remediation monitoring. Please note that this is the first of a two-part series titled Geophysics 101. So this webinar will be followed by a second webinar on July 28th. On today's call, Dr. Lee Slater from Rutgers University will provide an introduction to geophysical methods, and then he will discuss characterization versus monitoring and pre-modeling. Dr. Slater's presentation will be followed by a brief Q&A session. Then Dr. Judy Robinson, also from Rutgers, will provide an overview of electrical resistivity tomography concepts, followed by a second Q&A session. We will conclude the webinar with an interactive Q&A session with both of our speakers. Today's broadcast is listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. We do encourage you to submit questions well in advance of our Q&A sessions. On this slide, we provide a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. Many of you are already familiar with SERDP and ESTCP. For those of you that are not, SERDP is the Strategic Environmental Research and Development Program, and it was established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs, and they're really designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition of technologies to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally they do support some limited lab efforts. There are 4 programs in SERDP, 5 in ESTCP. The Energy and Water Program area is only in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Climate Change, and Weapon Systems and Platforms, are SERDP and ESTCP programs managed jointly by a designated program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. ER has essentially 5 main areas of research: contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see on this slide, our webinars cover a broad range of topics. with upcoming topics on water conservation, environmentally acceptable alternatives for fast cook-off testing, and assessment of redox-based groundwater remediation technologies. You can find additional information about upcoming webinars at this list. And with this, I would like to introduce our first speaker, Dr. Lee Slater. Dr. Slater is the Henry Rutgers Professor of Geophysics at Rutgers University in Newark, New Jersey. His current areas of research focus on geophysical monitoring technologies for tracking amendment delivery and long-term biogeochemical alterations caused by contaminant degradation. Dr. Slater has co-authored 135 peer-reviewed research papers and book chapters, including several on site characterization and remediation monitoring. Dr. Slater earned his doctoral degree in environmental science from Lancaster University in the UK in 1997. And with that, I turn it over to you, Lee.
Okay, thank you, Rula, and thank you everybody for being on the call and listening today. I'd like to start with an overview of the webinar. I'm going to be talking about geophysical methods. I'm going to say a little bit about the pros and cons of these methods versus more conventional invasive sampling methods for characterizing the subsurface. I'm going to talk a little bit about toolbox methods that we have at our disposal here for investigations, and introduce a few tools that we've developed as part of our tech transfer ESTCP project that hopefully will help the site remediation professional make a more informed use or decision around the application of geophysical methods. I'm then going to say something about two different ways to use geophysics for site investigations. One, characterization, and the second, monitoring. And specifically, I want to talk a little bit about methods or approaches that can be used to assess whether a geophysical method is going to be appropriate and hopefully avoid unnecessary expense on the use of geophysics when the method may not be appropriate. And in that specific instance, I'm going to introduce a few tools that we've been developing under this ESTCP project for tech transfer that we're currently working on. And as Rula already mentioned, there's a follow-on webinar in this series on July the 28th. My key message here is that these geophysical methods have great potential to reduce characterization and monitoring costs while improving results. But which methods to use should depend on the study goals and the site characteristics, and we want to avoid overselling of geophysics capabilities in site characterization and remediation. So if you're familiar with geophysics, you probably know some of the pros and cons. So the pros of these methods are they can be minimally invasive, they're relatively low cost compared to perhaps to drilling, you can cover a large area, and you can potentially see between boreholes, which are, as I said, more expensive and more invasive. But there's some cons here, and the geophysical methods are always indirect measurements of what we really care about. You may care about fluid chemistry, or you may care about contaminant concentrations, and with geophysics we're going to measure something that is probably perhaps going to be related to those factors, but not a direct measure. These methods offer limited resolution. There's no such thing as geophysical X-ray vision. There's no silver bullets. We cannot give you this image that you see on the screen here of the plumbing of the subsurface being revealed by this wonderful, miraculous geophysical technique. Instead, we end up getting images of the subsurface that have some limited information. They're spatially very extensive. They can provide information at depth from measurements just made at the surface, but they are smooth, fuzzy, if you like, renditions of subsurface structures. And we need to, when we interpret these measurements and when we use these measurements, and when we have geophysical contractors using these measurements, then we all need to understand these kind of limitations of these techniques. We have limited spatial resolution. The methods work best when they're combined with conventional measurements. So here, just to emphasize that point, if we combine geophysical sensing methods with direct measurements in boreholes, then we can potentially go a long way beyond our understanding of the subsurface plumbing, the movement of contaminants, for example, than we could possibly do based on just the direct measurements from the boreholes alone. So the toolbox is extensive, and I'm not going to bore you by reading through this list here. You've probably heard, if you look briefly through this list, you'll perhaps see some methods that you've heard somebody refer to, or you may, if you're a geophysicist yourself, you may have used. There are surface measurements, there are base measurements, there are measurements made using probes down boreholes, logging tools, these are more conventionally used. And there are measurements that are increasingly being used to image or provide information between holes by imaging across between existing or new boreholes that are drilled for this purpose. So there's a wide range of techniques at our disposal. And this second slide here on that issue just continues to make this point. There's a lot of techniques, a lot of methods available at our disposal. And one thing I want to do here is introduce shortly a few tools that the site remediation professional might consider using to evaluate what methods, given this extensive inventory of geophysical techniques, might be appropriate given specific site conditions and specific project objectives. One way that a geophysicist likes to break up these different methods is to link them to basically what we can physically measure. So here's a table now that kind of simplifies the toolbox of extensive geophysical measurements that are available into some key areas or key methods that are based on measuring a specific physical property. So for example, we're going to talk a little bit in this webinar about DC electrical resistivity, and this method senses the geophysical property resistivity, and electrical resistivity, the physical property, is controlled by a number of factors of the subsurface that include the water content, the salinity, the pore fluid concentrations, porosity, and so forth. And then there are various ways we can do these acquisition methods that allow us to apply these techniques, this specific technique. So this links the method to a property, to a relevant hydrological property or parameter that would be of interest to a site remediation professional. So it's a challenge, though. As a non-geophysicist, it can be a challenge. You may be aware of geophysics, you may have thought of using geophysics, but if you've not got extensive training in geophysics, you're struggling perhaps to figure out, well, what method would be most appropriate? Will this method work? These methods work under the ideal conditions for the method, and they often fail, sometimes dismally, when the site conditions are not appropriate or the intended application of the method is simply inappropriate. So we, and I say we because this project is a collaboration between Rutgers University and the United States Geological Survey Office of Groundwater Branch of Geophysics, have developed a tech transfer tool, which is an Excel-based tool, to help identify the methods that would perhaps address a specific project goal and are likely to work at a specific site given the site conditions, including the geological conditions, but also a little bit about the hydrological conditions and also the infrastructure, for example, the type of wells, boreholes that might be available. And the goal here is to provide project managers and regulators with tools for a numerical gut check to evaluate whether it's really appropriate to consider applying these geophysical techniques at a specific site and for a given objective. And this tool is available. It was recently advertised through a publication in Groundwater in 2015. It's available through a website, a USGS website. And you see just a screenshot here of the tool here. As I said, it's Excel-based, and it allows you to enter some parameters about your project and your site. So you can see some of the questions here referring to your specific site conditions. And then the other part of it is it asks you some questions about what your specific goals are. There may be some assumptions that we need to highlight. So you enter some information, you provide some information on your site and your goals, and then this spreadsheet will tell you, okay, we're going to give you some recommendations here, but we're making a few assumptions here. For example, if it's a borehole, we're assuming it's fluid filled. And then what the tool does is it provides just a matrix of methods that are likely to be appropriate and likely to be inappropriate. And the first thing this tool can allow you to do as a potential user of geophysics is really to evaluate what methods would be inappropriate, rule those out, and move on to those methods that make some sense given your project goals and also your site conditions. And we think this is an extremely valuable tool for the site remediation professional that's considering using geophysics. This tool could be used before speaking to a geophysical contractor, before going to somebody who's an expert, and considering being informed with your own information to at least have some idea about what methods should be reasonable to propose to address a specific problem at a specific site versus those that would likely end up being an unnecessary waste of money for little information content received. So I next want to talk a little bit about the goals of geophysics. So there's really two things that we do with geophysics. One is characterization and the other is monitoring. So characterization is all about really understanding subsurface spatial variations in, let's say, the lithology or the hydrogeological framework of a site. Perhaps you want to get a specific properties. You're interested in calibrating or informing some groundwater flow or transport model, and you need perhaps estimates of porosity or hydraulic conductivity. Perhaps we want to use geophysics to map the spatial distribution of dissolved solids or pore fluids if we're considering contamination. Perhaps we're interested in depth to water table or bedrock, for example. So these are all kind of things that we might use to do a geophysical characterization. These are the kind of targets. One thing we have to again emphasize is that we measure a geophysical property. No doubt, 9 times out of 10, the site remediation professional is going to be interested in not that geophysical property directly. They're going to be interested in a physical property that more directly relates to the hydrogeology or the geochemistry, and so we have to basically interpret these geophysical measurements in terms of a physical property or a geochemical property that's going to be of more interest to the site remediation professional. And so we can do this, but there are big caveats to this. We can do this. So these images on the right here show a geophysical realization of the subsurface electrical conductivity structure. That's the top image and the middle image. And the bottom image is those images translated into estimates of, in this case, the surface area to pore volume, which, if you're a hydrogeologist, you know is a factor that strongly controls hydraulic conductivity. And basically, the interpretation here is in terms of variations in coarse versus fine deposits across basically a small floodplain of a river. The interpretation now it shows where the coarse grained channel deposits are versus where the finer grained overbank deposits are. But this is an interpretation, and this translation that you see in this image here from these geophysical properties here to these to this estimate of this distribution of surface area is uncertain. I mean, this was done with an empirical relationship in this case. There is no direct relationship. There is no direct way to make geophysical measurements and directly provide images of, say, surface area or hydraulic conductivity, these kind of properties. We're always using some kind of what we call a petrophysical relationship, which will have varying degrees of robustness, and this needs to be considered in any geophysical interpretation. So in terms of monitoring, Judy's going to talk a little bit about some monitoring examples, but monitoring is a potentially very powerful geophysical methodology, and it's increasingly being used. So instead of just going to a site with a bunch of geophysical equipment and laying out a survey and collecting the data and walking away, we can actually install geophysical sensors permanently or for long term and acquire these data over time. And so in the same way that you might put a probe in the ground and leave it there to collect data over time at a point in the subsurface, and I think we all know the benefits of doing that. We get temporal information, and our understanding of systems becomes a lot greater. We can do the same thing with geophysics today. So we can lay out, for example, in this case, electrode arrays. We can install them, we can leave them, and then we can collect these geophysical images of the subsurface over time. And this is potentially very powerful because by looking at differences in the geophysical properties over time, then we can see where the system is changing. And so where, for example, fluids of different electrical conductivity are moving, then we can very easily track those changes with geophysical methods, assuming again the site conditions are appropriate and the method has been deployed appropriate for the specific goal. Whether you're doing characterization or monitoring, a key thing is to have realistic expectations. And so how do you actually quantify whether your expectations are realistic? Well, geophysics, all geophysical methods come today with methods and tool sets to allow us to do predictions or what we call forward or pre-modeling. So this is like with hydrogeological models. If you're a groundwater modeler, you know that you can set up a model and you can make some predictions. And we can do the same thing with geophysics. And it's a very important process. And if you're working with a geophysicist, you should encourage them to be doing this as part of their activities in terms of working at a specific site. So we want to predict what we will see based on a conceptual model. If we know we're looking to target a specific let's say contaminant, for example, we should have a conceptual model. And so here we've just developed a simple conceptual model here, probably not realistic, but just as an example, we've got some geology, we've got an LNAPL, we've got a DNAPL, and the question is, can we see this? It's the question the geophysicist often gets answered. The correct way to answer that is not just with some blurb and some arm waving, but to do some rigorous modeling. And there are various ways of doing this, different levels, different complexity. But these modeling tools really form the basis for survey design and interpretation and a decision about whether to apply the technique. So how does it work? Again, if you're a groundwater modeler, you'll be familiar with this process. We build a model. We assign the physical properties, in this case the geophysical properties. We generate the true model. And once we've generated the true model, true resistivity model rather, in this case, this is an example just based on resistivity. We've converted the conceptual model to resistivities of these different units. And then we can generate synthetic data. And so step 2 there, generate synthetic data. And then we can add even go as far as to add some errors, realistic errors to the measurements that we might expect given the site. And then we can take those synthetic data and see how well the geophysical imaging does to reconstruct the known model. And this is the process of inverse modeling, and the result of that there is this fuzzy image, as I explained earlier. And in this fuzzy image now, what we can see is that we have some justification for thinking that we should be able to see perhaps this LNAPL. You can see it nicely here. It's fuzzy, but you can see it. But the DNAPL, it's not so clear. In fact, I think you would agree that you really wouldn't be able to resolve this DNAPL down here. So these kind of tools are very important and should be used. Here's another example here of just showing how we use these tools to develop a conceptual model. Here's just a synthetic kind of model for a DNAPL spill, and this is just showing the effects of making measurements, geophysical measurements, just from the surface of the Earth versus would we improve things, how much better could we do if we had some boreholes to use at the site. And so we can test these concepts and we can inform ourselves about the basics of acquiring geophysical data, whether it's worthwhile given the site conditions and also the infrastructure available. Here's an LNAPL example, same idea, just testing whether we can again resolve this conceptual model before we go to the field. We do this. We want to see whether it makes sense to actually apply this method and spend the effort and the money based on some conceptual model for the site. One thing that I haven't shown here is that obviously these are all very simple models, and the Earth is a lot more complicated, and geological structure is complex and not as simple as I've shown in these models here. But we can model those kind of effects as well. We can perhaps use some kind of stochastic realization of the geological structure to put a bed background in now that might look more like a real geological structure at a site. And then we can superimpose again, our spill, and in this case we find that it's quite challenging to see the plume within the likely geological structure at the site, and this might inform us to decide to abandon the idea of using the geophysical measurement for this particular purpose. Monitoring is potentially very powerful because sometimes it's hard to directly detect features. So for example, if I just go back one slide, the problem here is we're trying to detect the plume amongst the background, and that's challenging, and here we see the geophysics start to break down. But if we do monitoring, and that means that we collect data perhaps before and after the movement of a plume, for example, this really allows us to overcome some of those issues of that geologic heterogeneity, and this is one of the great advantages of using geophysical monitoring. So here we see the needle in the haystack. So the left image here shows what's supposed to be just a plume. Okay, it's not a realistic plume, it's a circle, but it's a blob. Once we put the blob within the geology, we add the geology. So the middle image shows the geological structure. When we add those two together, the image on the right basically shows that in just the characterization image, we can't see the plume. So a bit like my previous example, we cannot see the plume because of the geological structure and the heterogeneity of the geology. But when we do monitoring, we collect data before and after. And again, if you're used to looking at time-lapse data, you know the power of that. And just the same with geophysics, we can difference these images, and when we do the differencing, then the geological structure is removed from the differencing, and I think you would agree that the location of the plume stands out very nicely. So recognizing that one of the techniques that's being extensively used at least in the DoD community for site remediation and characterization studies is resistivity, we've also been working on developing a tool that would allow the user, and again this is designed for a person with limited or almost no real strong background or any significant background in geophysics, to play around with testing whether a particular conceptual model for a site would suggest that it was worth using this particular geophysical method. So we're developing another Excel-based tool which allows us to do simple modeling of targets. So you can assume a little bit of geology, you can add a target that you're looking for, you can place it at different depths, and you can play around and get a feel for whether it even makes any sense to be using this particular geophysical method. And this tool is under development, and we're calling it Scenario Evaluator for Electrical Resistivity. So it's very similar to the previous Fractured Rock Geophysics Toolbox Excel-based spreadsheet I showed you. This one, again, is supposed to be simple and user-friendly. It requires no proprietary software, and it allows you, again, to predict the outcomes, the likely outcomes of a geophysical resistivity survey, given a hypothetical target and certain conditions about the type of measurements you're making or you can make, and specifics about the site. The template of the spreadsheet is coming with an example DNAPL plume, an example LNAPL plume, and blocks that allow you to make your own kind of subsurface targets, and this will be served again from the USGS website. So coming to the end of my half of the webinar, one thing we really want to do is reduce the misuse of the oversell of geophysical technologies. And we use resistivity as an example because resistivity is one of the technologies that's very easily oversold or misused. And we want to avoid that. There's this geophysical image I show here is unrealistic in terms of the geological structure that's being interpreted, and the suggestions that the geophysical measurement, in this case resistivity, is somehow linked to concentrations of constituents such as TCE or PCE has no physical basis, and it's really important to use these geophysical techniques within the constraints of what they are really capable of providing in order to avoid massive misinterpretation of data sets. So that really finishes up my webinar, other than to remind again that there is Judy Robinson is talking next about geophysical tomography, and we'll be back on July the 28th talking about borehole logging and more examples of case study examples of geophysical characterization and monitoring of remedial treatments that we've performed. And so again, the takeaway message here is that these geophysical methods have great potential to improve site characterization and performance monitoring while reducing costs. We want to emphasize that these methods do not stand alone. They complement one another, and they are not a replacement for conventional approaches. They should be used in unison wherever possible. Pre-modeling surveys are critical to ensuring that the geophysical technology is appropriately used. This is a really important thing for a site remediation professional considering employing a geophysical services contractor. We're working on developing new and user-friendly Excel-based tools that will facilitate that pre-modeling process and support informed method selection. And so I think this concludes my, no, not quite, I've got one more slide here just to summarize the benefits again. And that is the time and cost reductions, the expanded spatial temporal information, the fact that the measurements are minimally invasive, and the fact that we can make these measurements over many scales. That is one thing I didn't emphasize earlier. It's very scalable. These methods are very scalable. If you want to look shallow, we can do these measurements with sensors placed close together. If you want to look deeper but with less resolution, we can move these sensors further apart. So it's a these are very scalable techniques. And very importantly to finish is to acknowledge the team here. Fred Day-Lewis of the USGS is our lead from the USGS side of this project, and this is very much a joint effort between Rutgers and the USGS. Judy Robinson you'll be hearing from shortly, Neil Terry, Carol Johnson, and also Steve Hammett from NAVFAC, who has been supporting our efforts to get this information out to the right community. So I finished, and thank you for your time.
Thank you so much, Lee. I would like to remind our audience to submit questions by using that chat box on the left-hand portion of the screen. We have received a number of questions that we will pose to Lee, starting with the following. One of our attendees from the University of Pittsburgh would like to get a better sense of the timeline for the SEER tool. So can you tell us when that will be available on the USGS website?
We've done a lot of the development and the testing. We just need to really build the functionality of the Excel toolbox, and I think it's safe to say that this tool is going to be released by early fall, so September, maybe the latest early October.
Wonderful, thank you. One of our attendees from EPA would like to know what geophysical tool you would recommend for determining the diameter of a relic sinkhole in the Orlando, Florida area.
So whenever I get those kind of questions, there's always questions back, and then I would do some pre-modeling. So the kind of questions that the geophysicists will return with are, how wide is it, how deep is it, and so forth. But I will just say generally that karst and sinkholes have been very effectively tackled with resistivity, water or airfield, and particularly in Florida. There's many studies published of the use of the electrical resistivity method to image sinkholes, and so it's a starting point. But I would to suggest that would be a candidate technology. But again, we would want to consider, before going to the field, doing some conceptual pre-modeling.
Thank you, Lee. Another question, can you please comment on the regulatory acceptance of geophysical data and interpretation as part of conceptual site models or for demonstration of remedial performance?
Yeah, that's a great question, and my impression is there is none. These methods, standard practices and so forth, and Q&A of geophysical data is problematic. And I think that it speaks to the fact that these methods provide indirect information. And so indirect information there's always a massive danger of misinterpretation, and I think that as these techniques become more and more used, we're going to have to address some of these problems and develop methods for regulatory acceptance of the technologies.
Great, thank you. Another question. Where would you recommend finding case studies of applications of geophysical methods for site characterization and monitoring?
Right now, they're dispersed. Obviously, there's a lot of geophysical literature, and there are journals that focus more on case studies. The Journal of Applied Geophysics is one. You will find them in case studies that might be relevant to the site remediation community in the journal Groundwater, sometimes in Groundwater Monitoring and Remediation. This is being addressed right now through a parallel tech transfer project that is working on developing a wiki. And the wiki is going to have a geophysics entry that's directed specifically at the site remediation community, and it's going to have a very extensive inventory of case studies that are relevant to the DoD site community. But for now, I think it's really a matter of looking through the more applied geophysical journals, such as the Journal of Applied Geophysics.
Great, thank you. And the wiki project that Lee is referring to is called, there'll be a web page called Remediapedia, and it will have a number of articles, summaries on the state of knowledge of different tools or technologies. So Lee, when do you expect your article to be ready?
Our article is written. It's going through USGS review right now, which is always a bit of a hold-up. But we're in the process of getting the review taken care of.
All right. So what we'll do for now is we'll go ahead. I'll send everybody on the call the link to current to that website, and you can keep an eye out for Lee's article when it does become available. Lee, can you please tell us if there are open source tools available for pre-modeling?
Yes, there are. Some of many of the tools are available open source for the modeling step or for limited use. Even some of the commercially available tools, they will provide them in limited form to allow you to do modeling and exploration with obviously limited capabilities for looking at larger data sets. But there are also academic use tools that are available for the different geophysical techniques for that specific purpose, as well as interpreting your own field data, but they tend to be more challenging to use as a non-expert relative to tools that are commercialized and wrapped up into a user-friendly GUI and so forth. But this is the reason why we're developing this Excel-based tool for this specific purpose. It will be resistivity. It will focus on resistivity, but we have already had discussions about developing similar tools for other geophysical techniques if the demand is there.
Great, thank you. I have a question for you from the chemical industry. As a client, what should I look for when I hire a geophysical company?
That's a good question. So I think that you obviously can look for examples of successful uses of geophysics. I mean, there's certainly people who have had specific experiences with different companies and contractors, and so I think talking to your colleagues can help. But I really think that one of the best things to do is ask the geophysical contractor if they're proposing to do a survey for you at a site to demonstrate through some conceptual model that you can help them by providing information on the site and your goal that it's a feasible approach. And any good geophysical services contractor will be able to come back to you, will be able to spend a few hours developing a few synthetic scenarios like I showed you here. And any geophysical services contractor that doesn't do that or is reluctant to do that, then I think that would be a major flag with respect to employing them.
Thank you, Lee. You showed examples of 2D and 3D geophysical surveys. When is 2D acceptable, and under what scenarios are 3D surveys needed to understand the subsurface?
So the state of the the state of the method, the advances in the method have led to the abilities, or most geophysical methods have led to the abilities to collect now three-dimensional data sets. And of course the Earth is inherently three-dimensional, and there's always the danger of misinterpretation. There's many caveats to the geophysical images, and we often forget that when we're presented these images, like I showed you, the two-dimensional images, that we're making a huge assumption about the Earth, that the Earth is a two-dimensional, has a two-dimensional structure. That means those features in those images that I was showing in 2 dimensions are assumed to extend infinitely in the direction into your screen, into the direction perpendicular to that image. And of course, anybody knows that that's extremely unlikely. If you do subsurface investigations, you know this is not the case. If you can do three-dimensional geophysical imaging, then you're overcoming those limitations. These techniques are now available to be used in 3 dimensions, but often 2-dimensional surveys are still the state of the practice by the geophysical contractor, and it's very important to remember what those limitations of those those 2-dimensional imaging surveys are. When a 2-dimensional imaging surveys are appropriate or more realistic, when the Earth is more likely to approximate that. So if you're running a survey across a site that you know is extensive in one direction, and you want to get a cross-sectional view, but you know that it's a pretty, for example, a plume, and you know it's pretty extensive down gradient, then maybe there you're pretty safe. You can assume that the 2D assumption is approximately okay given the purposes of your study and your specific site.
Thank you, Lee. One more question before we transition to Judy's presentation. Can you tell us if there are differences in the instrumentation used for geophysical characterization versus long-term geophysical monitoring?
Some of the methods are really well developed for, or well suited for the monitoring. Some of the techniques are not. So, like, for example, if you're familiar with a method like ground penetrating radar, which has been extensively used over the years, it's not really a tool that can be used for monitoring because the sensors are expensive. They're electronics that need to sit at the site, and so it's not practical to leave them in place for long-term monitoring. But other methods like resistivity are really well suited for monitoring because resistivity uses very simple sensors. It uses pieces of metal as electrodes attached to wire, and these can be distributed across a site and left. I know of places where these sensors have been left for years and have been used to continually acquire resistivity data sets.
Great. Thank you, Lee, for a very clear presentation and for handling the questions so beautifully. The next part of this webinar will be presented by Dr. Judy Robinson. Dr. Robinson is a research associate at Rutgers University in Newark. She has extensive experience collecting, analyzing, and modeling large 2D and 3D surface and borehole ERM data sets. Her current area of research involves the use of lab-based geophysical methods to extract hydrogeologic properties that control flow and transport from fractured rock cores, while comparing these measurements to borehole geophysical data. She earned a doctorate in environmental science from Rutgers in 2014. And with that, I turn it over to you, Judy.
Thank you very much for that introduction, Rula. So for those of you who are continuing to join us, Lee pretty much went over an overview of geophysical technologies, and this talk really focuses on using electrical resistivity tomography. So just to go over the agenda, first I'm going to talk about overcoming limitations of traditional hydrogeological characterization, and then I'm going to focus on electrical resistivity tomography and talk about concepts and field implementation. I'm going to talk about guidelines to a successful field campaign, and then give a few surface and borehole examples. And the key message I'm going to try and convey is when used appropriately, ERT can help resolve the hydrogeologic framework controlling flow and transport at your sites. So it's not really, the idea here is not to limit you from using traditional hydrogeologic sampling, but to add ERT to your toolbox of tools to characterize your sites. And it may provide indirect information on subsurface transient processes. So there are challenges in characterizing your sites, and boreholes are expensive. You have to spatially interpolate between these discrete samples. And the sample volume that you get from cores or borings may not reflect the subsurface heterogeneity. In addition, drilling creates unwanted hydraulic pathways, and you may connect units that you would otherwise not want to be connected. So geophysical characterization, Lee went over this quite extensively. It can provide improved spatial coverage. It's minimally invasive, particularly for surface surveys or if you're using existing boreholes. And it can be cost effective. It can reduce your site characterization costs. However, it's of limited resolution. Resistivity or conductivity must be linked to the parameter of interest. Quite importantly, you cannot directly measure contaminant of a concentration through these methods, so it has to be linked to resistivity or conductivity. So again, it's another tool that you can use in your toolbox, and it's most powerful when interpreted jointly with other geophysical or hydrologic data. So what are our goals of geophysical characterization? Lee had actually had this very similar slide to this. So if we have 2D or 3D distributions of resistivity and another parameter here called chargeability, we can then take that data and come up with either a site-specific petrophysical transformation, or we can come up with something from the literature, and we can use that to convert that into an interpretation that we are looking for. But there's definite uncertainties in these petrophysical transformations. But here, what I've done is convert distributions of conductivity into distributions of S-pore, which is surface area normalized by the pore volume, which is a key hydraulic parameter. And here it's being used for a geologic interpretation in order to show where channel deposits are as opposed to overbank deposits. So what is electrical resistivity tomography? You can think of it as the geoscience equivalent of medical imaging. So if we have somebody's knee or somebody's skin and we wrap electrodes around it and we want to collect measurements at different configurations, we can then use some type of transformation to determine what is happening beneath someone's skin. Well, the same is true when we go out and do an electrical resistivity tomography survey. So typically, I see a typo. Typically, what we do is we inject current in 2 electrodes, and then we measure the potential in another 2 electrodes. So typically, it's a 4-electrode measurement, and we can do this in a bunch of different electrode configurations. So I'm showing here a Venner array, which is a nested array, or a dipole-dipole array. And these measurements are sensitive to water content, porosity, lithology, temperature, as well as groundwater composition. We can then take these resistance measurements, and knowing the electrode configurations, we can solve for a geometric factor, which is denoted there as K. And we can come up with apparent resistivities from our raw data. And with the apparent resistivity, we can have an idea of resistivity or its inverse conductivity magnitudes in the subsurface, as well as an approximate spatial distribution of these parameters. But if we truly want to get the spatial distribution of resistivity or conductivity in the subsurface, we have to apply inverse methods in order to do that. So how do we actually go out and collect how do we collect our data? Well, in the surface, that means that we put metal stakes in the ground, stainless steel metal stakes. We can connect them through clips to a central cable. In a borehole, that means we can have a central tube and we can hook our electrode around that tube and then connect a wire to it. But for borehole electrode arrays, we can have a very simple array, as I just showed you, which is just the clamp, a hose clamp around a center tube, a PVC pipe, and wires running to the surface. Or we can have a more complicated array. So on the left-hand side, I'm showing something that was used in fractured rocks. So we wanted to isolate different sections within the borehole. So we have packers. We also wanted to do amendment injections and water sampling. So there's a water sampling line where we can do that. There's also air lines that connect to the different packers. So really the borehole electrode array, the design can complement the field application. So we can take our surface cables or our borehole wires and we then bring them to a central enclosure or a central location where we hook them up to our resistivity meter. Our power source is shown here. Here we're using 3 batteries. And we can also hook up a laptop where then the whole operation can be operated either on-site or remotely. So here's just one example of an installation we did, which is a 3D ERT surface array. We have 196 electrodes at this location, and we did a custom-built cable for this. So we have 20-gauge wire inside that split loom, and at each electrode location we have the wire popping out and just connecting to those electrodes through a simple banana plug connection. They all go to that central enclosure. And at this site, we were using solar panels in order to charge our batteries. So as Lee mentioned, we can also use geophysical technologies, and in particular ERT is very well suited for monitoring applications. So we can change something in the subsurface, like inject an amendment, and we can then take data at each different time step. So what we end up with is a bunch of images, static images, which are dependent upon, again, lithology, water content, porosity, temperature. And so what we can do in order to look at this in our time-lapse ERT inversion is we can invert each of our time-lapse steps back to our reference model. And then when we view our results, we can subtract off that background inversion. And so it really focuses on imaging the changes in the subsurface. So it's a good way to image an amendment injection, and I'm going to show a couple examples of that later on. So next I want to talk about some guidelines to a successful ERT campaign. You really need to ask yourself, what is the depth and spatial extent of the intended target? So there are some general rules of thumb. First of all, as the electrode spacing increases, the depth of penetration increases. Lee had mentioned that these are actually scalable, and this is because we can get more information as we increase our electrode spacing. However, the resolution of features decreases. The second rule of thumb is as the resolution of features decreases as the distance from the electrodes increases. This means for a surface survey, with depth, our resolution will decrease. And for a borehole survey, as I'm showing on the right, what that means is our model sensitivity to the field data is the lowest in between those borehole locations. We can limit that effect by making our aspect ratio, denoted here as D over H, less than 0.75. It's also important to what type of survey you're going to use. So nested arrays are typically better at resolving horizontal layering. Dipole-dipole arrays are better at resolving vertical contacts. However, you have a lower signal-to-noise ratio with a dipole-dipole array. However, many systems are able to collect dipole-dipole data much faster than nested arrays, particularly in multi-channel instruments. So it'd be really nice to go out to a site and be able to collect a complete, comprehensive data set of all the different electrode configurations that you can possibly have. But we all have a limited amount of time, so it's likely that the time you have available will determine how much data you collect. Additionally, there may be spatial and instrumentation limitations at the site. So by spatial, it's just how many electrodes can you fit at a site, and you may also have power limitations. So I strongly suggest doing some type of simulations or forward modeling at your site, and Lee also spoke about this quite extensively. So if you know what your conceptual site model is, so say you know you have a vadose zone, which is shown here as a highly resistive layer, and then a plume beneath that vadose zone. Will your electrode spacing and your measurement sequence be able to resolve an expected model? So it's very dependent upon how many electrodes you have and the sequence that you use. So it will give you a good idea of what you can expect in your model. So here's another example where we have a resistive body and just showing what happens in the synthetic result as this resistive body is moved up in the surface. So this was done with 100 electrodes at 1 meter spacing with a combination of Venner and dipole-dipole measurements. And you can see that this resistive body is not really resolved when it is below 15 meters. So this gave a pretty good idea of what to expect. You could, if you wanted to increase your depth of penetration, you might increase your electrode spacing, or you might just change your sequence, and that might change your results as well. So next I'm going to talk about 3 contaminated sites where ERT was used. So first I'm going to talk about a surface example and then go to 2 borehole examples. So first I'm going to talk about the Hanford 300 site in Washington State. It was contaminated with uranium from the storage of spent nuclear waste up until about 1987. So previous studies have shown that this contact between the permeable Hanford formation and this relatively impermeable ringhold formation is a critical hydrogeologic unit which controls flow and transport of uranium from the site to the Columbia River. And this fine-grained unit is a thin subunit of fine-grained material. So 2D ERT profiles were collected parallel to the Columbia River at an increasing distance from the river. And it was non-invasively, these lines are non-invasive, and it was done to delineate the boundary between that Hanford and ringhold layer, those 2 layers. So the ERT measurement is affected very much by lithology. So it was thought that given the sharp change in lithology, this contact boundary could be identified. So the conductivity of 3 of the lines are shown on the right, and the distance from the river increases in the images from the top and the bottom. So I'm showing just lines 0, 2, and 4. And you can see that there's a clear boundary between the upper, more resistive layer and a bottom, more conductive layer. So overlaying on these 2 profiles is the boundary between the Hanford and the ringhold formation identified from those 2 wells shown there on the left. And it agrees well with the ERT results. So this information was then used to interpolate a surface that represents this Hanford ringhold contact. And here the blue color represents an area of lower elevation of this contact. So drawn in a black dotted line is an inferred paleochannel pathway, and this represents a possible contaminant pathway from the site to the Columbia River. So what you see along the river are the results of a fiber optic distributed temperature sensing survey. And this data was collected during a low river stage, so presumably lower temperatures likely represent exchange of the groundwater to the surface water. So at the outlet of that proposed groundwater surface water exchange pathway, the temperature is lower than other areas on the profile. So this supports evidence of a discharge of groundwater to the river at this location. So in this study, ERT was able to delineate a critical hydrogeologic unit, the boundary, which controls flow and transport from the site to the Columbia River. Next, I'm going to talk about 2 borehole examples. The first is at the Naval Air Warfare Center, which is a fractured rock mudstone site. And the objective at this site was to use 7 ERT dedicated boreholes to delineate hydraulic pathways to determine where an amendment injection was going. So first we had to generate a characterization image in order to compare all of our monitoring results to. And a lot went into creating this image. We used what's called an informed inversion approach. So we used all of our, any borehole data we had, such as borehole deviations. We used maximum and minimum fluid conductivities within the boreholes. We had an idea of the strike and dip of the formation from our coring. And we also had maximum and minimum boundaries on just our bulk conductivity of our mudstone. When we do this, when we look at this characterization image and we compare it to the optical televiewer logs, which were done for all these boreholes here I'm showing two, we can see a pattern of alternating massive and layering. And this is partly because of the geology at the site. So we were confident that we were characterizing the site pretty well. So we did an amendment injection of molasses spiked with sodium bromide to increase the conductivity contrast between the host rock and the injection. And we started injecting at this outer borehole, and then we injected, we waited, and then we did ERT imaging. And we did that until all of our injectate was gone. So we started at 87 BR. It migrated down to the center borehole, 83 BR, and then kind of turned the corner over to 85 BR. And this last image here, T7 and T8, are somewhere around 60 days post-injection. So we still had a little bit of a conductive signature, and that plume is actually between 83 and 85 BR in the direction of 84 BR. So in this study, we were able to really monitor the movement of a tracer without affecting the hydraulic gradient, because we literally just injected and then did our ERT imaging at a scale that we wouldn't have been able to achieve just looking at borehole sampling alone. So the last site I want to talk about is Brandywine. So until 1987, this site was used to store waste and excess governmental materials. And the objective at this site was to use hydrogeophysical tools to remotely monitor and visualize subsurface amendment, placement, and transport in near real time. So over here on the right, I'm showing the monitoring system in true dimension. So you can see we have water sampling wells at 3 distinct ports, ERT and sampling wells, electrodes in both the boreholes and at surface locations. So in biostimulant amendment, they used here a proprietary amendment called ABC, and then later a molasses injection. And the idea was to monitor the distribution of the amendment over time and to verify these results with auxiliary measurements. So the verification goals of this project required a lot of extra sampling wells, as you can see here. So for a typical monitoring application, we wouldn't need so many. This is a shallow application, so surface electrodes were used here to complement the borehole information. ERT dedicated boreholes will certainly add an additional expense, but the wells don't have to be finished as other wells do, and they can be very narrow. So they'll be much less expensive to drill. So let's take a look at some monitoring results. So here over on the left, I'm showing the background characterization image, and it reveals the overall geological and geochemical setting. So the image is consistent with what was found during the well installation. So we can see a high conductivity deep zone shown as the confining unit, a low conductivity intermediate zone of coarse grained sands, and a shallow intermediate conductivity zone corresponding to fine sands and silts. So the time-lapse results over on the right begin after an initial injection of an amendment and are shown for 6 months afterwards. So the amendment is shown to have migrated laterally along that confining unit within the coarser grained sands of the aquifer. So at about 6 months post-injection, the dilution begins to occur and the site is beginning to restore back to the pre-injection state. So the goal of monitoring amendment placement was continuous here. It was automated, and it was done for over a year. So all this was just left in place, and then remote monitoring was achieved. So because of time constraints, what I've presented here is really a subset of each of these studies, and if you're interested in learning more about any of these applications, please contact me and I can send you the journal information where you can read more about all of these applications. So finally, some takeaway messages. I hope I've shown you that ERT can help define the hydrogeological framework and structures controlling groundwater flow and transport. ERT can be another tool that you use in your toolbox for site characterization. It can detect proxies of contaminants and transformations, but cannot visualize contaminant concentrations directly. So your parameter of interest must be linked to conductivity or resistivity. And the benefits, again, I hope I've shown that there are time and cost reductions. Hopefully by doing this you can reduce your typical costs of site characterization by including ERT, as well as there's definite expanded spatiotemporal information. It's minimally invasive, and the scale, as Lee had mentioned, you can collect this information at different scales, but it can be appropriate for parameterizing flow and transport model, which is really the next step in moving forward with this data. I'd like to acknowledge other people on this project: Lee Slater, who you already heard from, Fred Day-Lewis, and Carol Johnson of USGS. This project is really a joint effort between Rutgers and USGS, and Neil Terry of Rutgers University. And with that, I'd like to thank you for your time and open it up for questioning.
Thank you, Judy. We have received a number of questions. For borehole ERT, do wells need to be dedicated to ERT arrays? And can electrodes for ERT imaging be used in monitoring wells?
So the wells do not have to be dedicated to just collect ERT. We've done a couple of applications where we've looked at strapping electrodes to casing in wells, the casing or the slotted interval or the casing, and then just strapping it around and running the wires to the surface. So they don't need to be just ERT dedicated boreholes.
Great, thank you. Can you tell us how effective ERT is for characterizing and monitoring separate phase contaminants, or NAPL, before and during treatment?
That's an interesting question. It really depends on, we're really looking for a conductivity signature, so it really depends on the conductivity contrast that you're seeing within the ground. So if you want to see changes over time, I guess you can see changes in the conductivity, as it degrades. So I guess a NAPL typically has a conductive signature, and then over time that will degrade. But yeah, is there another question?
Yes. For an amendment injection, what conductivity contrast do you consider reasonable to image with ERT?
So the higher the contrast, the better, but I would say at least a factor of 10 conductivity contrast between your existing groundwater fluid and what you are injecting. So if you don't have that type of contrast, you can always spike your amendment with some type of conductive additives such as sodium bromide or calcium chloride, calcium bromide. Yeah.
Great, thank you. A question from the EPA.
Okay.
How many hours of field work were needed for the Riverside example? So how labor intensive are these measurements?
Well,
and setting up to take these measurements?
Well, if you're doing a surface survey, it's labor intensive just to put the borehole array down. or not the borehole array, the surface arrays in the ground. For a borehole survey, you can always build your electrode arrays beforehand. If you're attaching it to monitoring wells and you're using the casing on the site, it might take a little extra time to install that casing on the site. I would say the real time is in collecting the data. And I would say that that far outweighs actually putting your electrodes in place.
Great, thank you. One more question, please. Can borehole ERT be used above the water table in a dry well?
So the way we achieve contact between the electrodes and the formation in a borehole is often through the fluid in the borehole. So if you're going to do this above the water table, you need to have some contact with the formation. So in that case, you may have to actually backfill your borehole in order to get that contact with the formation. But it is possible, yes.
Great, thank you. How important is understanding data noise when creating ERT images, and how can field data noise be estimated?
So understanding your data noise is actually quite important when producing these images of conductivity or resistivity, because it can have a large effect on your image in what you are actually able to resolve. So one way that you can actually estimate data noise in the field is by doing reciprocal measurements. So repeatability is not shown to really be a good indicator of noise in the field, but collecting reciprocal measurements whereby you inject current into electrodes and read potential into electrodes. If you actually reverse your injection, where you're injecting and where you're reading your potential, the difference in those measurements can give you an idea of your data noise. So it's just important to have an idea of that for your modeling, because if you overestimate your data noise, you can get overly smooth images, and if you underestimate it, you can get really rough images. And you just want to make sure that what you're interpreting is representative of what's actually in the field.
Thank you. A question from the U.S. Army Corps of Engineers. Were induction or normal resistivity logs used as part of the ERT configuration and optimization phase? And if not, why?
Are you talking about for a particular project?
Maybe for the two examples that you cited, Judy?
So for the NOC project, we looked at the borehole geophysics first before we moved forward, even in designing our borehole arrays. So we did use our normal logs in order to have an idea of what the conductivity was in the subsurface. So we could plan to have a certain amount of contrast as well when we did our amendment injection.
Can I just add to that? I'll just add that we can use the logging data if it's available to constrain the inversions away from the boreholes. So if we have logging data from traditional logging tools, those measurements can be used to actually help the inversion between the boreholes to provide more realistic structures beyond the boreholes that actually honor what we see at the borehole with the logging tool.
Thank you so much, Lee. And perhaps this is a good time to pull you back into the Q&A session. So let me ask you some questions that both of you can attempt to answer. If I'm approached by a geophysical contractor proposing to solve my subsurface problem using geophysical methods, what would be one or two good questions that I should ask of the contractor to evaluate whether their approach is realistic? Can we start with you, Lee?
Yeah, I think I would ask the contractor to demonstrate that they can actually resolve the target of interest through some conceptual modeling exercise. So to achieve whether this particular method is or approach or application is realistic, really That's really the aim of this pre-modeling exercise, and I think that would be the key question I would ask the geophysical contractor is, can you demonstrate to me using some synthetic models and using some available numerical modeling that this is a feasible thing to be considering doing.
Judy, would you like to add anything?
No, I mean, I think the synthetic modeling is important. It's important to, a lot of geophysical contractors will say they're able to resolve a particular feature when they're not really sure that they're able to even do that.
Thank you. And can you both tell us what strategies can be used to better evaluate the information content within a report on geophysical surveys that is produced by a geophysical contractor? Lee, maybe we could start with you, please.
So some of the things to consider is, again, whether any pre-modeling was done to evaluate proof of concept, whether the noise in the data has been carefully assessed and actually presented, and whether the processing of the data set is fully transparent. Because one of the problems with geophysics is basically that junk in equals junk out. If we put bad data in, we get images, we get realizations of subsurface structures, but they're contaminated by the junk that's gone in. And the problem is the non-expert just has no way of assessing that. So some data quality metrics, some assessment of how much structure in geophysical images comes just from the noise levels in the data. These are all things that can be easily done, and a really good geophysical contractor will be considering.
Judy, would you like to add anything?
Yeah, I would also add that if a contractor is making interpretations or about concentrations of contaminants, that just cannot be the case. So I would just be weary about images, ERT images that just show too much structure. Is there really a valid reason to show that much structure? I hope now you have an understanding that these images produce a limited resolution. So when you start seeing very sharp features, you really have to question whether that's from the data or not, or if they're just over-interpreting the data.
Great, thank you. Back to you, Lee. In your DNAPL and LNAPL pre-modeling examples, why were the contaminant plumes shown as electrically conductive targets?
Yeah, and I think there was a question for Judy on that as well. It's commonly known now. It was a bit of a surprise in the 1990s when geophysicists were first working on some of these LNAPLs and DNAPLs. Everyone expected them to be resistive targets because it's a non-aqueous phase liquid. I mean, if you look at the actual electrical properties of an LNAPL or a DNAPL out of the can, so to speak, then it's very resistive. But biodegradation and natural attenuation and transformations of the LNAPL in the subsurface or the DNAPL in the subsurface invariably lead to mature sites, mature contaminant plumes at sites being actually electrically conductive compared to the surrounding environment.
Thank you so much. For you, Judy, you showed examples where ERT was successful in a field application. Are there any field applications where you would not recommend using ERT?
So certainly if you're doing a monitoring application, you want to make sure the conductivity contrast, especially for an amendment injection, is going to be sufficient that you can actually image a difference. There has to be a contrast in the subsurface, even if you're going to do a characterization image. Are you looking for a lithological boundary? There has to be some contrast for you to image. The other thing is for a borehole survey, sometimes people want to come in and do a survey after the fact, after the boreholes have already been put in place, and consideration of an ERT survey, maybe it just wasn't considered at the onset of putting in these boreholes. So once that aspect ratio gets above 0.75 or much above it, you're really limiting your capability to image in between those borehole locations. So maybe if that was quite large, that aspect ratio was quite large, it might be better almost to do a single borehole survey rather than try and do some type of cross borehole survey.
Great, thank you. A question from NASA. Are there any depth limitations to using ERT in a borehole, Judy?
Are there any what limitations?
Depth.
Oh, depth limitations. In a single borehole?
Yes.
So you can space your electrodes however far you would like to space them. So you can go, they can be a meter apart, they can be 1.5 meters. It depends how much space you have within your borehole. And within a single borehole, there's no limitation. It's just how many electrodes do you want in the borehole, how much space do you have, and what that spacing, how far do you want to image into the formation with your electrodes. So as your electrode spacing increases, you can increase your depth of penetration into the formation. But there's, yeah.
Maybe I can just add there as well, Rula, there's also no real limitation on how deep we put in the sensors. These electrodes are very simple. People have been now using these methods to look at geothermal reservoirs 3 kilometers or so down. And the same techniques are being applied. It's the nice thing about this particular technique is what goes in the borehole is pretty simple stuff, and can be ruggedized to go into very deep boreholes if that's the area of interest.
Great, thank you. I'd like to expand a little bit here on the questions about space. How much space on the surface is necessary for the ERT equipment? For example, can ERT arrays be easily installed at active industrial facilities or active military installations?
Is the question about the fact that there's a lot of infrastructure or safety issues? Can I just get a bit of clarification on that?
Yes, both.
I'm probably not quite following the exact specifics of the question here. There are problems with these methods, with most geophysical methods, when there's a lot of infrastructure, and the sites then become very geophysically noisy. So this isn't just for DoD sites, but for many industrial sites where these methods are utilized, they can become challenging when there's a lot of stray electrical currents floating around from various site activities. This is particularly problematic for the surface-based measurements where you're obviously close to all this infrastructure. A lot of the borehole measurements that we make, even though we might be at a very, very nasty industrial site with a lot of electrical equipment and a lot of things going on, once we get the electrodes down deeper in the hole and we're doing this cross-hole stuff, it becomes insignificant. But certainly the surface surveys and many of the geophysical surveys that we use have definite challenges when your sites are highly industrialized with lots of electrical currents floating around from various power supplies and things like that. I'm not sure if that was the direction of the question, but that's an important thing.
That was the direction, because you showed photos of areas that were completely filled up, for example, with cords. So if you have an active site, can you really leave these cords lying around on a driveway or in a building? Or would that preclude you from using these tools?
Well, I mean, if you're going to leave your cables out, I mean, you have to be concerned with wildlife even if you're in a remote area. But just, some sites can just have security concerns where you really wouldn't want to leave your cables lying out. So, it depends. I mean, you want to make sure it's secure, your site.
Great. Thank you, Judy. And one last question for you. There was some lack of clarity about the resistivity contrast that is minimal to expect success assuming conditions and survey design are suitable. Can you just repeat what you said with regards to the resistivity contrast, please?
Sure. It's best to have the highest contrast possible, but I would say a conductivity contrast of about 10 would be suitable.
Wonderful. One last question before we wrap up. And before we wrap up, Lee, I would just like you to briefly go over the topics for the second webinar in this series in July. So before you do that, let me ask Judy, how would the choice of remedial amendment affect the results from ERT imaging, please?
So using electrical resistivity tomography, we're really concerned with the conductivity or resistivity contrast. So as long as you can always take your amendment and take it to the lab along with a groundwater sample and to get an idea of what that contrast is going to be. So different amendment injections have different conductivities. So it's just important to understand for your particular amendment what that contrast is. And if the contrast is not enough, you could always spike it with something conductive, such as sodium bromide.
Great, thank you, Judy. And Lee, can you please tell us very briefly about the July 28 webinar?
So that will focus on, it will be a two-part webinar again. The first part, I believe, is going to be given by Carol Johnson, who will be talking specifically about these borehole logging tools and introducing not just established tools, but some emerging new technologies. That's her real area of expertise. So those will be borehole logging technologies, and many of these have been used relatively routinely, but there are new technologies that have become online recently with more ability to say something more about the subsurface characteristics, particularly the pore geometric properties controlling fluid flow. And then the second part will be really a kind of example of what we consider some of the best case study example applications of the geophysical technologies in terms of characterization of contaminated sites and then monitoring of fluid transport with a focus on, again, amendment in monitoring, injection and monitoring.
Great, thank you so much. So again, this webinar will be offered on July 28th. Registration is open on the SERDP and ESTCP webpage. And before we conclude, I'd like to remind everyone that our next webinar is on Thursday, July 14. It will focus on water conservation issues and will feature two speakers. The first one is Catherine Ostapek of the Navy Region Southwest, and the second is Gary Angiano of the Environmental Security Technology Development Branch at NAPAC. So registration is open for this webinar soon, so please visit our SERDP and ESTCP webinar webpage to register for this and other future webinars. I would like to remind you before we conclude that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for your time.
Thank you. Please stand by.